Hello friends, let's continue our discussion on discontinuous control modes. Okay, so we were discussing discontinuous control modes, right? And the first discontinuous control mode was on-off control mode, which we discussed the last module. Okay, and we talked about something called a neutral zone. Okay, neutral zone. Okay. Is really important because without neutral zone, an on-off controller or a two-position controller would not work. So we discussed this uh, two-position or on-off control mode. Okay, so both are the same. Okay. In the previous module we were discussing this, and then now we just extend it to multi-position control mode. What does it actually mean? Okay. It actually means that instead of having just two positions, we could have multiple positions. Okay. Let's assume that we have three position control mode. What does it actually mean? So in such a case, what would happen is, let's say I am looking at three positions. Okay. I'll just write this as three positions of controller corresponding to an error corresponding to an error. Okay. So in this case, for example, if you see here, if the error is greater than the value E2, you have the controller output to be 100%. If the error is in a certain range, minus E1 to E2, of course these are some arbitrary values which are given here, but in actual process, there could be different values. Okay, so we have 50, 0, and 100. Okay, three values are given here for a certain range of errors. Okay, so this is a three position control mode. So what we see here is that if you look at this plot here, so you have the control output, you have the percentage of error here. So from this plot, what we can ascertain is that in this range, for example, if the error stays in this range of plus or minus E1, you have a control output of 50%. Okay, if the error is exceeding E1, the control output is 100%. If the error is exceeding minus E1, you are getting back to a control output of 0%. Okay, so there are three different types of control outputs for three different ranges of errors. Okay, so therefore it's called three position control mode. And of course, therefore, it's in generalized terminology, you can call it as multi-position control mode. Okay. Now, how does this actually work? Let's check it with an example here. Okay, so you are looking at a three-position control action. Let's try to understand with an example here. Now, to understand with this this concept with the help of an example, you need an error plot, which is really important to understand. Okay, first, if you have an error plot, and if you see the perturbation of the error around zero, then you can actually sketch the controller output. You can sketch the controller output. All right. If we are trying to map this controller output with respect to the error plot given. Okay, so this is what we are trying to do now. Okay, we're trying to map the controller output with respect to the error plot given. So we need to sketch this plot. Okay, how does it come up actually? Okay, so let's say now this error curve, when it is in the range of from here to here, from 0 to this value, you can see the error curve is in between minus E1 to plus E1. So if you go back and see, if the error is between the range minus E1 to plus E1, you have the control output of 50%. Okay, that means you can see that from these 2 points, 1 to 2, you have the controller to be at 50%. Okay, now let me see between 2 and 3, let me mark this 0.4 and this 5, okay. So between 2 and 3, what should happen? Now it is exceeding the error E1, okay. It is exceeding the error E1, the control output should be 100% as per this graph, okay. So between 2 and 3, you should see to it that you have the controller output to be 100% here, okay. So assuming that there is a small lag in the control action, you can show it as a slanted line here, okay, which can be plotted by the little ramp here, okay. Most practical controllers will have slight delay, which can be shown as a ramp here. They may not immediately respond, okay. Okay, so this is the way it is shown here, okay. Now between 3 and 4, again you are coming into the band of plus E1 to minus E1, so your controller output remains at 50%, okay. So it has come back to 50 from 100, okay. Now from 4 to 5, it has exceeded the lower limit of minus E1. Lower limit of minus E1 means that you need to have the controller output to be 0, okay. So you are coming back to 0. Of course, with the delay you are having a little ramp in this control output here, okay. Now again, after 5, you have this error entering the band of minus E1 to E1, so therefore you are getting back to 50%, okay. So this is the way you should be able to plot the control output given an error curve like this, okay. This is the given error curve, okay, and this is the control output, okay. So if the controller has some delays, you need to show it with a ramp so that the output is reached with a small time delay of delta t, okay. This could be called as a delay time or lag or whatever it is, okay. So you could have called it as a lag or a delay and so on, okay. So this is all about the multi-position control mode, okay. Now next we get back to another discontinuous control mode, which talks about some kind of integral action here, which says that if you have the rate of change of maybe other way I can put it here, that if you have delta EP greater than a certain threshold, okay, then you are increasing your controller output at a certain rate, okay, at a certain rate of plus or minus kf, okay. That means if the error is exceeding plus delta EP or minus delta EP, you are changing the rate at which the controller increases its value or decreases its value, okay. The rate at which the increase in value of the controller or decrease in the value of controller is dictated by the thresholds plus delta EP and minus delta EP. And now this, you can see clearly here that kf is constant here, okay. Kf is constant here, so therefore this is a single value of kf, so I am calling this as a single speed floating control mode. There is a reason why we are calling it as floating control mode here, that we will try to explain in the subsequent slides, okay. So what happens, we are looking at the rate of the change of control output, and this is the percentage of error. If you see that if you are in this band of plus delta EP to minus delta EP, in this range the rate of controller is 0, okay. That means if the error is falling within this band, the rate is 0. That actually means the controller output will be constant, okay. Controller output P is actually equal to some constant, okay. That means whenever the error becomes 0 or falls into this band of plus or minus delta EP, the controller will hold on to the last value because it's an integration, okay. dp by dt is equal to 0 means that P is equal to integration of 0. That actually means that you are holding on to the last value of the control output, okay. So this is in some sense a stepping stone for an integral control, even though a single speed floating control mode may not be exactly replicating the integral action, but it is a good way to analyze how an integral control will work. Okay, so this is the way it works now. So let's try to understand this single speed floating control mode with the help of an error curve and the control output. So this is the error curve, and corresponding to that you have the control output here. Okay. However, here we are talking about a reverse acting controller. That actually means that if error is increasing, control output P should decrease. If error is decreasing, control output P should increase. Okay. If this is the case, if error and the controller output are opposite, okay, then I would call that control action to be a reverse acting controller. Okay. So any control action you can define it as direct or reverse. Okay. Direct means if the error is increasing, control outputs increase. Okay. It actually depends on the situation we are in. Okay. The type of process we are in and the requirements of the process. Okay. So here if you see, as I told you before, that if I am in plus or minus delta EP range, I should be having the control output to be 0. Okay, dp by dt should be 0, not control output 0. Okay, so from point 1 to 2, let me just put some points here. Okay, now between 1 and 2, you have plus delta EP to minus delta EP. That actually means dp by dt is equal to 0. That means the control would hold the past value before it entered this one. Okay, so that means you are having some initial value of controller P of 0. Okay, now once it exceeds the limit here at plus delta EP, okay, that means error is getting positive, more and more positive than plus delta EP. You are decreasing the control action at a certain rate. So this rate is Kf, or that means it is minus Kf to be precise. Okay, so you are decreasing the rate at which the controller is going down, control output is going down, that is minus Kf. Alright. Again from 3 to 4, you have the error to be within the band of plus delta EP to minus delta EP. So in this case, you are holding on to the last value of the controller, which is here, just before entering the band of 3 to 4 or plus delta EP to minus delta EP. You had the control output to be so much here. The same value will go up to the next value, next error bound. Okay. Now between 4 and 5, what you see is the error is exceeding minus delta EP. So since it's a reverse acting controller, you again need to increase at a rate of plus Kf. Okay. And then after that, you are getting back here system to normal. So plus or minus delta EP band. So therefore, you should hold on to the last value. Okay. This is the last value. So you see that there are several places wherein the control is floating here. Here it is floating and also here, right? So whenever you see that the error is within the band of plus delta EP to minus delta EP, controller is holding on to the last value because of the governing equation of the controller, which is plus delta dp by dt is equal to plus or minus Kf. Alright. So this is the way this floating mode control works. So fundamentally, this is like a single speed floating mode controller. Okay. So logically speaking, if you wanted to have multiple speed floating control mode, then what would you say is that why can't I keep this value changing? Okay, change this value. Okay, so if you think logically here, so what if the error bound is higher? Okay, then Kf should be higher, right? Kf can be higher if delta EP is higher. Okay, so you can have multiple ranges of delta EP. Okay, the higher the range of delta EP, the larger the value of Kf, for example. It makes sense because so larger the error band, okay, the rate at which the controller output should either increase or decrease, okay, should depend on Kf. Okay, the same concept has been applied here in the multi-speed floating control mode. Okay, so here you see that dp by dt is 0 in this error band. Okay, this error band here. Okay, And now, as the error band is increasing up to some value, the rate is given as plus k1 or minus k1. Okay. If the error is increasing much more than that, the rate is increasing further. Okay. If the error is increasing, that means from the nominal error, if you are increasing further, that means the rate at which the controller output is increasing is much higher. So that means delta EP is higher, Kf is higher. Kf is K1 is less than K2 is less than K3 and so on. Okay. So if we have infinite number of such levels here, okay, if we have infinite number of such steps, then the multi-speed floating control mode would be equivalent to the integral control mode. As we'll see later, that a multi-speed floating control mode with infinite number of steps, okay, infinite number of gains based on the range of delta EP would be equivalent to, not even approximate, would be equivalent to an integral control mode. We see this in subsequent classes. Okay, thank you.